So today we're going to learn about molecular formulas. So what is a molecular formula? Well, it's actually just another name for the chemical formula of a molecule. Let's say you have a chemical like glucose. It has a chemical formula of C6H12O6, and that is also its molecular formula. The molecular formula tells you how many carbons, how many hydrogens, and how many oxygens are in glucose. In this case, there's 6 carbons, 12 hydrogens, and 6 oxygens. Today we're going to learn how do we actually create a molecular formula. And there's 2 pieces of information you need to make a molecular formula. You need the empirical formula. That tells you the ratios of each element. And you also need the molar mass of the whole compound. So, for example, the empirical formula of glucose would be CH2O. It's this ratio that means you've got 1 carbon for every 2 hydrogens for every 1 oxygen in glucose. We'll also need to know the molar mass of glucose itself in order to figure out that molecular formula. So let's try a couple of examples. Our first example will have a pretty simple empirical formula. It's just CH. So that means you've got 1 carbon for every 1 hydrogen. That's what your empirical formula is telling you. It's that ratio of carbons to hydrogens. We also need to know its molar mass. So the molar mass of this whole molecule is 78 grams per mole. So that's the molar mass. We want to find the molecular formula. So we start by just writing down what we know. We know the molar mass of my whole compound. So I'm going to use the symbol of capital M to represent molar mass, but I'm going to be writing down 2 molar masses here. So I need some sort of subscript to differentiate which one am I talking about. First, I'm talking about the entire molecule, the actual compound itself. So I'll use the subscript molecule to indicate that. So the molar mass of my whole molecule is the 78 grams per mole that I'm given in the problem. Now, what's the molar mass of my empirical formula? Well, that's not directly given, but I can read it off the periodic table. The periodic table tells me that the molar mass of carbon is 12.011 grams per mole, or some periodic tables round that off to 12.01, which will totally work as well. And that the molar mass of hydrogen is 1.01 grams per mole, or 1.008 if I want to be more precise. So I'll do that one. So let's put those 2 together with my empirical formula. I have 1 carbon in my empirical formula, right? That's CH means C1H1, a ratio of 1 to 1. So I do 1 times the molar mass of carbon. And I have 1 hydrogen, so I do 1 times the molar mass of a single hydrogen, either 1.008 grams per mole or 1.01 if you want to round it off, that'll be fine. That gives you your molar mass of the empirical formula as 13.019 grams per mole. All right, so I've got these 2 molar masses. What do I do with them? Well, the key step in finding a molecular formula is we have to find that scaling value that we're going to multiply all of our subscripts by in order to scale it up to the actual molecule. Right, so the empirical formula is just CH, right? So 1 carbon, 1 hydrogen. But maybe the scaling factor is 5. I don't know. If it's 5, then this would scale up to C5H5. Or maybe that scaling factor is 20. Then this would scale up to C20H20. That scaling factor, we're going to call it X. And X is always a whole number, and it's the ratio that I've got to multiply every subscript by in my empirical formula in order to scale it up to the molecular formula. How do I calculate X? It's actually pretty simple. I just take the molar mass of the entire molecule and I divide by the molar mass of my empirical formula. So that right there is the key formula I'm going to use to calculate X, which is the scaling ratio that takes me from an empirical formula, which is just the ratios of carbons to hydrogens, in this case, up to the molecular formula, which is actually how many carbons and how many hydrogens are really in this molecule. We do it by just doing molar mass of our molecule divided by molar mass of the empirical formula. So in our case, the molecule has a molar mass of 78 grams per mole, and the empirical formula had a molar mass of 13.019 grams per mole. So we divide those out, and I get X equals 6. So that means my scaling factor is 6. It means I'm going to take my empirical formula, C1H1, and I'm going to multiply each of those subscripts by 6. That's the thing that I scale it up by. That actually gives me a compound called benzene, which is C6H6. So that's what I have here. Let's try another example. Here's one where I'm not actually given the empirical formula. I'm just given the percentages of sulfur and the percentages of bromine in this compound. But I'm also given the molar mass of the whole compound. So if we need those two pieces of information, molar mass of the whole compound, we've got that, right? So here's the molar mass of my whole compound, 223.94 grams per mole. And then the other key piece of information I need to get a molecular formula is the empirical formula. Well, then what I'm going to need to do, I'm going to need to actually go through the whole process of getting an empirical formula first, and then my last sort of new step on top of it will be finding the scaling factor X. So what do? If I want to find an empirical formula, my first step is to assume I've got 100 grams of my compound. And I do that just because it makes the numbers really nice. If you've got 100 grams of your compound and 28.64% of it is sulfur, then your mass of sulfur must just be 28.64 grams. And so we'll use a subscript of S for sulfur, and the symbol for mass is lowercase m. Same idea with bromine. If you've got 100 grams of your compound and 71.36% of it is bromine, then my mass of bromine is just going to be 71.36 grams. All right, so I've got my masses of each of the elements in my compound, but it's not masses I need for an empirical formula, it's moles. So I'm going to need to convert these to moles. And to do that, I use my very fun equation. Moles is mass divided by molar mass. I'll do that for each of the two compounds that I've got here. So first, sulfur. The number of moles of sulfur will be the mass of sulfur. So that's what's on top here. Mass of sulfur on the top. And on the bottom is the molar mass of sulfur. And how did I know the molar mass of sulfur was 32.066 grams per mole? Well, I read that right off the periodic table. So that's that molar mass written right on your periodic table. Do that division, so 28.64 divided by 32.066, and that gives me 0.893 moles. Now we've got to do the same process for bromine. So bromine has a mass of 71.36 grams, and the molar mass of bromine is 79.904 grams per mole. And I read that again right off the periodic table. Do that division, and I actually also get 0.893 moles of bromine. So my next step will be to take those moles and write it out as an empirical formula with the number of moles of each element written as subscripts. So here we go. The subscript after sulfur will be 0.893 because that's the number of moles we have of sulfur. And the subscript after bromine will be 0.893 because that's the number of moles we have of bromine. We need whole numbers in an empirical formula, so we always divide each of those subscripts by the smallest subscript, whichever one is smaller. Now, in this case, they're actually the same, so we're going to divide them by 0.893 because that is the smallest. We divide both subscripts by the same number, we divide them both by 0.893, and that makes 1, right? 0.893 divided by 0.893 is going to be 1. So our empirical formula is just 1 sulfur to 1 bromine ratio. Or we could write that as just SBR. When you have ones as your subscript, you don't have to write them. But what it means is you have a ratio of 1 sulfur for every 1 bromine in this compound here. All right, but we're not done, right? That just tells me the empirical formula. What I need to find is the molecular formula. So I now need to do that new last step that we've just added, and that is to find the scaling factor that I have to multiply both of those subscripts by in order to scale it up to whatever it is. Maybe it's actually S7, B7, who knows? We'll find that out soon. So I'll write down my empirical formula, SBR. I've put the ones in just to make it super obvious. Then I write down the molar mass of the whole molecule. So big M for molar mass. Subscript molecule, meaning that this is This is not my empirical formula molar mass. This is the molar mass I'm actually given in the question. That's the molar mass of my real compound. I can figure out the molar mass of my empirical formula pretty straightforwardly. In my empirical formula, there's 1 sulfur, so I put 1 sulfur in, and I multiply it by the molar mass of sulfur, which is 32.066 grams per mole on the periodic table. There's 1 bromine, so I take 1 bromine and multiply by the molar mass of bromine on the periodic table, 79.904. Add those two together and I get 111.97 grams per mole. Then I have to find that X value, which is the ratio that I'm going to multiply my subscripts by in order to scale up my empirical formula up to the molecular formula. And that ratio is just the molar mass of your whole molecule divided by the molar mass of your empirical formula. In our case, that's 223.94 divided by 111.97, which is just 2. So that means my scaling factor is 2. I'm going to take those subscripts, S1, BR, the R is not a subscript, sorry, BR1, and I'm going to multiply both of them by 2. And so I get S2, BR2. And that is my compound there. So disulfur dibromide, S2Br2. I'm going to do one more example with you. This one is another tricky one. So we know its overall molar mass, 203.49 grams per mole. But again, I didn't give you that empirical formula. I gave you just percentages. In this case, it's a hydrocarbon, so it's just made of hydrogen and carbon. We've got 17.37% hydrogen and 82.63% carbon. We want to find that molecular formula. So my first step here is to think, okay, I've got to find an empirical formula first because I need both the molar mass and that empirical formula to get the molecular formula. My first move in getting an empirical formula is to assume I've got 100 grams. So assume 100 grams. If you have 100 grams of this stuff and 17.37% is hydrogen, then the mass of hydrogen must be 17.37 grams. And if I've got 100 grams of stuff and 82% is carbon, then 82 or 82.63 grams must be the mass of carbon that I've got there. But remember, an empirical formula doesn't want masses, it wants moles. So we're going to need to use our fancy formula, moles. Not an M, got carried away. Moles here is the mass divided by the molar mass. And we'll use that formula here to figure out the number of moles of hydrogen and the number of moles of carbon. So the number of moles of hydrogen will be the mass of hydrogen, which was 17.37 grams, divided by the molar mass of hydrogen. And we read that right off the periodic table. So this is the mass of hydrogen. This is the molar mass of hydrogen right off the periodic table. Some periodic tables will say 1.008. That's fine too. Either, it won't make a big difference at all. So do that division, 17.37 divided by 1.01, and that gives me 17.198. So that's the number of moles I have of hydrogen. Now I do the same thing with carbon. The number of moles of carbon will be the mass of carbon divided by the molar mass of carbon. So that on top there is the mass of carbon, and on the bottom, the molar mass of carbon in my periodic table. So the mass of carbon, 82.63, divided by the molar mass of carbon, 12.01 grams per mole. And that gives me 6.88. So there are 6.88 moles of carbon. Your next move is going to be to write down that empirical formula, but write it down with subscripts that are the numbers of moles. So we've got C, carbon, and then the number of moles of carbon is 6.88. Oh, that's not very clear. I will use a better color. C, 6.88, there's my number of moles of carbon. And H, 17.198 is my subscript there. Next, I need to make those whole numbers, and I do that by dividing by the smallest subscript. The smallest subscript is the 6.88, so I'll divide this by 6.88, and I'll divide this by 6.88 as well. So 6.88 over 6.88 is easy. That one's 1. The other one, 17.198 divided by 6.88, is going to give me 2.5. So just carry this on over here. So I'm currently at this stage. The empirical formula is C1H2.5. That's actually not allowed for an empirical formula. You can't have a decimal in an empirical formula. So we have to look at what do I need to multiply both of those subscripts by in order to scale them up to the nearest whole number, whatever that is. And that multiplier is going to be 2, right? I'm going to multiply both of those subscripts by 2. And that gives me an empirical formula of C2H. 2.5 times 2 is 5. So that right there is the empirical formula. Which is great, but I'm still not done. I need to actually find the molecular formula. So for that, I'm looking for X. X is the ratio of the molar mass of my molecule, my real molecule, divided by the molar mass of my empirical formula. The molar mass of my molecule, I can actually read out of the question. So that is that 203.49 grams per mole that I was given in the question. And the molar mass of your empirical formula is going to be 2 carbons, so that's 2 times the molar mass of carbon, 12.01, plus 5 hydrogens, so 5 times the molar mass of hydrogen, which is 1.01. So adding those up, 2 times 12.01 plus 5 times 1.01, that gives me an empirical molar mass of 29.07 grams per mole. Let's put that together to calculate X, that ratio. So my whole molecule molar mass is given in the question, 203.49 grams per mole, divided by my empirical formula molar mass, which I just calculated, 29.07 grams per mole. So do that division, 203.49 divided by 29.07, and you get a ratio of 7. That means I'm going to multiply each subscript in my empirical formula by 7. So here's my empirical formula, C2H5. I'm going to be multiplying each of those subscripts by 7 in order to scale this up to the molecular formula. 2 times 7 is 14. So this scales up to a subscript of 14 carbons. And 5 times 7 is 35. So therefore, the molecular formula is 14 carbons with, made a little mistake there. The molecular formula is, we'll try that again, 14 carbons with 35 hydrogens, and that is how we find a molecular formula.